Hello, PCCL channel greets you. We speak of nuclear fusion when two light atomic nuclei fuse together to form a heavier nucleus. There are fusion reactions in the stars, therefore in ours, the Sun. There are some in the H-bomb, H like hydrogen. And, if the project is successful, in the ITER program reactor near Kaderj, I am going to use the nuclear reaction which will take place in this reactor to illustrate what a fusion reaction is. There will be deuterium and tritium in this reactor. These are indeed light nuclei since deuterium is the isotope 2 of hydrogen. That is to say, it has a neutron in addition to the hydrogen that we know in chemistry, which is H11. Tritium is the heaviest isotope of hydrogen, having a mass of 3. It has one more neutron. So, 3 nucleons. We can write tritium with the letter T, and deuterium with the letter D. When they merge, they give a lot of energy. A helium nucleus, or alpha particle, it's the same, and a neutron. Here is the equation here. With deuterium, tritium, helium, neutron. Why is there so much energy when this nuclear reaction occurs? Well, if I could compare the nuclei of the reactants with those of the products, I would find that there was a loss of mass during that nuclear reaction. Appearance of energy, loss of mass. Are these two observations not linked? Yes, it's Einstein who answers with his famous formula here. E equals mc squared, where c is the celerity of light, speed of light expressed in meters per second, don't forget the square, the variation of mass in kilograms, and therefore, quite naturally, the energy will be found in joules. We'll see that. The speed of light. I take 3 times 10 to the 8 with 2 zeros to have 3 significant digits. Eventually, you could get 4. Follow the instructions. Ask your teacher. An example of an exercise that we are going to do together. If you are asked to complete the nuclear reaction here, as if I had not yet explained anything to you, what will accompany the helium? There must be conservation of the number of nucleons. 2 plus 3 equals 5, there are 4. So here there is going to be 1, you have already found. Number of charges, 1 plus 1 equals 2. Here, there is a 2, therefore here, it's 0. This particle is the neutron since it is a nucleon which is not charged. The next question will be to calculate the change of mass. You'll not be left alone. To accompany this question, the masses of the different protagonists will be given to you. If it's in kilograms, it's easy. You do, final minus initial, as for each variation. And you find yourself. Quite naturally. If the instructions gives you the masses in atomic mass units, don't panic. Look for that relationship in the statement. Don't memorize it, it will be there. At that point, you do the same, final minus initial. Except that you will have a result first in atomic mass unit. You use the conversion relation here to have the result in kilograms. For sure, you will be asked to calculate the released energy. Perhaps you will be helped with a precision on the expected units. You have known the relation E equals mc squared for a long time. The speed of light, here, I talked about. You get a result, first in joules. Then you use a converting relation. One more. Be careful. There, it's from MeV to joules. Therefore, If I wanted to convert from joules to MeV, I'll have to divide to get 17.6 mega-electron-volts, most of which will be carried away by the neutron. Two words on the experimental conditions. This could be the sectional view of the ITER reactor here, which is shaped like a tire. The cut would be made there. So, inside the reactor, light cores of deuterium and tritium. But there is no fusion reaction yet. They don't merge because they are both positive. So, they tend to repel each other. Plus and plus. They have the same sign. In order for them to merge, it will be necessary to provide them with energy. That is to say that it will be necessary to increase the temperature of the plasma. I am commenting on the word plasma here. It is like a gas except that the particles, at such temperatures, are dissociated. That is to say that there will be the nuclei on one side, the electrons on the other, without there being what we could call neither atoms nor molecules. So, these nuclei are confined by a magnetic field so that they do not touch the material wall for the reason that they must maintain a very high temperature. By touching the wall, the plasma would cool, and the merger would stop. The wall, for its part, would see its integrity considerably damaged by such temperatures. For the reaction to start, I said, it will be necessary to go up to 150 million degrees Celsius, so that the kinetic energy of the nuclei increases. At that moment, the Coulomb barrier is crossed and the reaction is possible. You see the helium nuclei, the alpha particles, but you don't see the neutrons. Well, the neutrons left with most of the energy, as I was explaining, and they went through the magnetic field. Why? Well, precisely because they are neutral. That is to say that they are not electrically charged. So the magnetic field doesn't do anything to them. They will therefore interact with the wall of the tokamak, and the reactor, to heat water, for example, which will be the water for the cooling circuit, which will drive a turbine, an alternator to produce an alternating voltage, as in conventional thermal power stations. Eventually, I believe that this is part of the project, to ensure that these neutrons, too, interact with lithium which would be placed in the wall because, a neutron on lithium, that can produce tritium. So the reactor would produce its own fuel. Deuterium, there will still be it for 6 million years in seawater. So that's not a problem. That's it for this video. Thank you.